All right, I'm going to go over a problem from the Chapter 8 homework, which is conveniently very well laid out and tells you exactly what to do. The main problem with this is going to be getting your sines and cosines set up properly. So, a body of mass m and negligible size starts from rest and slides down the surface of a frictionless solid sphere of radius r as shown below. First, we need to solve for speed v as a function of angle r. Using conservation of energy, find an expression for v in terms of the given quantities m, r, theta, and or gravitational acceleration g. So, to start out with conservation of energy, you say that the initial kinetic energy and the initial potential energy is equal to the final kinetic energy and the final kinetic energy and the final potential energy. So there is no initial kinetic energy because it's starting from rest, 1/2 m times 0 squared. But we can come up with a ideal for the initial height. So if we start writing the height, or if we start the height from the center of the sphere, then the initial height is just going to be the radius r. So we set this equal to m times g times r, and we have the final kinetic energy, which we're trying to solve for. We're trying to solve for v. uh, plus the potential energy at any given point. So in order to solve for the height at any given point, we're going to call this y. You need to only find the projection of r along the y-axis. So height is going to be y, which is going to be r cosine of theta. Because the y-axis is uh because the y-axis is adjacent to the angle that we're making, we use cosine instead of sine because this is equal to r times adjacent over hypotenuse, which is just because r is equal to the hypotenuse, y is equal to r times adjacent over r is just equal to the adjacent side of the is just equal to the adjacent side of the triangle, which is just going to be equal to r cosine theta. So using this, we can actually cancel out all of the m's, g, y times r cosine theta. Cancel out the m's. G r minus r cosine gr cosine theta is equal to 1/2 v squared, or v squared is equal to 2 gr times 1 minus cosine of theta, or v is equal to the square root of 2 gr 1 minus cosine theta, which if you've done a lot of conservation of energy problems, you'll recognize as just the general form of velocity for an object that is only in a gravitational field. It isn't in anything else. It's 2 gr delta y. The next piece we need to relate is relating the forces to the block. In order to uh, relate forces to the block, we want to find the objects or find draw a free body diagram and find how much each of the forces relate to the block. So in this case, N is pointing out and weight mg is pointing down. And we need to solve for the equation of how much these overlap with the point, with the line that's going towards the center of the circle. So N is obviously pointing out from the center of the circle, so it's going to have when we find the radial forces, the forces that are pointing in towards the center of the circle, N is going to have a negative value. But mg has some component that's pointing towards the center of the circle and some component that's not. Therefore, mg is going to have some component there. So starting out doing some trigonometry, we find theta is equal to this angle over here, meaning that this angle is 90 degrees minus theta, meaning that this angle is theta, because the angle that it makes with respect to the radial axis is going to be all three of these angles of the triangle have to equal 180 degrees. So since you have a right angle, then these two angles, this one and this one, have to equal 90 degrees. So that's 90 degrees minus theta. And because the weight is perpendicular to the horizontal, you're going to end up with theta. You're going to end up with theta being equal to 9, or theta plus this angle that we just found being equal to 90 degrees. So 90 degrees minus theta plus, we'll call the angle alpha, is equal to 90 degrees. Alpha is therefore going to be equal to theta when you do the algebra. So when you set up the forces in the radial direction, you end up having mg cosine theta being the projection along the radial direction, because again it is adjacent and not opposite. So when we find the projection along the radial direction, we are looking for the adjacent side, which means that we use cosine minus normal force. And then putting A and B together, this is equal to mv squared over r, which is going to just be the r that we found already. It's not going to be, because it's rotating around the sphere, it's not going to be any projection into the x or y axis. It's just going to be the total r is going to be our, uh, yeah, the total r is going to be our value for r in this case. So F radial equals mv squared over r. We want this, this means that n, or mg cosine theta plus minus n is equal to mv squared over r. Uh, n is then equal mg cosine theta, adding on both sides, is equal to mv squared over r minus n or plus n. So n is equal to mv squared over r minus mv squared over r plus mg cosine theta. And we know that at some point these are going to, uh, as mv squared over r becomes bigger, then the normal force is going to become smaller, even as mg cosine theta is going to become smaller as well. So at some point, this is going to equal zero and it's going to lose contact with the sphere. So at that point, mg cosine theta is equal to mv squared over r. Cancel these out. G cosine theta is equal to v squared over r, which is going to be equal to 2gr 1 minus cosine of theta divided by r. So the r's are going to cancel out. R over r is going to cancel out, and you can also cancel out the g in both of these cases. So you get cosine theta is equal to 2 1 minus cosine of theta. So 2 cosine of theta or 3 cosine of theta is equal to 2, or cosine of theta is equal to 2/3.